Thanks, and thanks for inviting me. I really look forward to this hackathon. I'm going to talk a bit about Hakyll, which is a static site generator, and I will just do a simple overview and tutorial, and then hopefully we will dig into the internals a bit and see how it all works, in particular how the dependency handling works. So a bit about me. My main hobbies are skateboards, photography, and of course Haskell. I really like Haskell. I've been doing open source Haskell since I was at university. I've worked with Haskell for some companies now, and I'm currently working for Fugue, which is a cloud orchestration company, and we have our own DSL, which we wrote in Haskell. And all the tools around it, like the compiler, some other things are also in Haskell. Yeah, so first I'm going to introduce static site generators generally, what they are, what you can use them for, then talk a bit about Hakyll, give a tutorial, and dig into the dependency handling problem a bit. So let's talk about static site generators. What are static site generators? You know, back in the day when I started out messing with the computer, things were fairly simple. If you wanted to have a web page, you just wrote some HTML in a text editor, you uploaded it, and you were done. Or you could have like a bunch of files, you all uploaded them, and you were done if you wanted, and you were doing good practices. You could even put them in SVN or something. And generally, it was a much simpler time, and everyone was happy. Until something horrible happened, and everyone started using things like Drupal and Blogger and WordPress, which is totally fine for some use cases. But I think in general, these sort of applications are a bit overused because most of the time people just really want like a stupid simple site, right? A stupid simple website. So to solve this problem, there are static site generators. There's a shit ton of them. Hakyll is one of them. I hope to think it's one of the better ones. But yeah, so if you enjoy this talk and you enjoy the idea of static site generators, but you don't really like Hakyll for some reason, maybe check out another one, but preferably Hakyll. The basic idea is that you still write your blog post or your content, your pages, in either HTML or Markdown, which is a bit simpler than writing HTML. You usually can have some metadata, and you can do some simple formatting. This applies to pretty much any static site generator out there. So after you write your content, you usually write some sort of template. The templating language varies in between static site generators, of course. Some things have more features, some have less features. But generally, you end up with something like this, and then you perform the build through your static site generator, whatever that command that is, and you end up with something like this in a separate directory, which you can just upload to your website, and you're done with it. So I think this has like a lot of advantages over, say, Drupal or WordPress. The first advantage is that it's insanely fast. If you just have some static HTML files on your web server, someone visits the page, there will basically be one system call to send file, and the user will get the page served. Especially if you sort of like embed assets like CSS and whatnot into the HTML file. Hakyll provides some tools to do that. And this is much faster than, for example, WordPress, where if you visit a single page, you need to go to the database, you need to load the comments, and that sort of stuff. And this has other implications because, for example, Google really likes pages that load fast, so you end up higher in the ranking. And secondly, there's some more modern tools as well to help you deal with static content, to sort of like distribute it geographically. Not that that is necessary for a simple blog, but you can also build more complicated things. And like all these advantages apply to static site generators in general, right? So not Hakyll in particular. Another big advantage is there's no vulnerabilities, well, outside of Apache or Nginx, of course, or whatever you're using to serve your website. But yeah, you can't go in and like do like weird XSS hacks or like SQL insertions because it's just simple HTML and there's no interactivity whatsoever. Another advantage is that pretty much any host supports it. This is probably the reason why I first wrote Hakyll, actually, because I think my university had some sort of deal with a hosting provider, but the hosting provider only provided Windows hosts. So I couldn't run, I don't know, WordPress or Rails or whatever I wanted to run on my host. So I decided to, okay, I should just go with like a simple static site. Then I started digging into static site generators, and I found out there wasn't a decent one yet, so I had to write Hakyll. But yeah, the hosting support is really cool. You just need to be able to serve static HTML files. And secondly, you have version control support. This is really great, like if you have a mistake or you can easily revert. People can send pull requests, for example, if you make a typo. This is not the case if you're using WordPress or something like that. If you're just writing custom code, you might have version control, but it won't be as convenient as having static site generators. Another big advantage, you can use Vim, your favorite text editor, to write all your posts, and even then you can choose what sort of language you write your posts in, because usually they support a bunch of things like plain Markdown, HTML, or even like LaTeX or Emacs, org mode, or those kind of things. And using Vim or Emacs, if that flows to your board, is generally better than using like the crappy, what you see is what you get editor that comes with these CMSs. Like I think this is the one from Wikipedia, which is not too bad, but like it's just so much easier, especially for us programmers, to write Markdown. Yeah, so a bit about, more specifically about Hakyll. It's been around for quite a while for a Haskell project since 2009. It's built upon Haskell and Pandoc. Although Pandoc is optional, you can also use another tool to convert your post. It's very configurable since it's written as a library. So instead of having a configuration file, you just have a main file which ties everything together. This can be very short or very long, depending on what you want. So that's a nice thing. If you want to do really complex things, it's possible. If you want to do easy things, it's very simple. And because the whole configuration is in Haskell, you can, of course, use any Haskell library out there. If you want to do some image things, you can use Juicy Pixels. If you want to use, you can use other graphics libraries. You can use system.process to shell out to other tools like Compass or Less or something to compress CSS. So all in all, it's very, very extensible. Yeah, so let's give a quick tutorial/demo. And for this, I'm going to be using, so GitHub recently improved the sort of support they had for static site generators. So I wanted to show that. So I'm just going to create a new repository, and I'm going to build like a very simple photo blog, like this. There we go. And we start off by cloning the whole repo. So we now just have an empty directory. Hakyll provides a tool to initialize a new website, which just gives you an example configuration and some random files. I think this is fairly useful because you don't have to go through the tutorials to figure out everything you need. In this case, it's going to generate much more than what we need, actually. but it's easier to throw things away than to add things, so I'm just going to use it anyway. As you can see, it created, so site.hs is the name of like the main configuration file. It's sort of the convention to call it site.hs. Then we have some CSS. We have an index page. This is sort of a template actually. We have like some images. We have an about page, some sample blog posts, and then some templates. Finally, a contact page, and then also a cabal file. And you can see it named the project after the directory, which is neat. So if we look at the site.hs, this is a sample Haskell configuration file. So it starts with the main, it imports Haskell. I guess we don't need the mapend import anymore. It's a bit old, so it's a declarative DSL, and we have a bunch of rules for different things. For example, this is how we process images. This is how we process CSS. Both things consist of a route and a compile. The route tells you where things go. This is simply ID route, which means the ID function from Haskell, which means that images/foo.jpg goes to the final output/foo.jpg. And we compile specifies how you want to change the content or process it. And in this case, for images, we just want to copy them over. For CSS, it's the same ID route, but we want to compress the CSS. There's a bunch of different routes, and you can combine them. For example, here we have set extension. Then we have a more complicated processor, where we first call pandoc, and then we use monadic bind to sequence it with some more things. For example, applying a template and relativizing URLs. Let's browse a bit more. Like this is the example site. So there's a bunch of things in there. And we will start deleting them soon. But let's first make one edit. So if we look at the GitHub support for static sites, you can see right here, GitHub pages. There's multiple options to host it. And the one we want to use is to use the master branch/docs folder. So in order to use this, well, it's sort of grayed out right now. We need to push our content to it, and we need to make sure we have a /docs folder. So we're going to do that. And the way we're doing this is we're going to have, so instead of like, this is what we call in Haskell, like the rules. Tells you how your content gets processed. And additionally, you also have a configuration which allows you to tweak some global options. We're going to be using that. So we need to declare it. And we're going to use the default Haskell configuration. And we're just going to tweak one option, which is a destination directory. There we go. Normally, Haskell uses the _site directory, but in this case, we want to use the docs to have support for GitHub pages. Now we just compile the main file. I'm not going to use Cabal in this case to make things very simple. There we go. And now we can do a site build, and Haskell compiles our entire website. You can see there's a bunch of things here. And for example, if we edit one page, you can see it does the incremental build well. And we're going to dig into how that works a bit later. But now let's prove that it worked. For some reason, it didn't generate into the docs directory, but it generated into site, and I know why that is. It's because we declared our configuration, but we haven't plugged it in yet. So this should be better. Now I'm just going to remove the site and do a full rebuild. There we go. So if you look at docs, you can see everything is generated there. We have the pages, like the about.markdown is renamed to HTML, that sort of thing. We have all our posts. So now I'm gonna make a quick git ignore. I don't want the cache. I don't want site, which is the executable. I don't want the HI file, and I don't want the O file. And other than that, we can ship it all to GitHub. And let's see if we can use the GitHub Pages support now. Okay, does it give me the link? It says site not found. Let me check. We have a docs file.
I believe it can take some time.
Yeah, it's probably, oh, there we go. Yeah. So that works fine. And we have the example page up on GitHub. Now, often you don't want to upload everything until on your host and then check it using that, because presumably something is wrong as well, and other people can also go to your website. So Hakyll sort of provides a built-in server called Watch, which both watches the content. So if we now do a quick edit of the About page again, delete this paragraph, then it's picked it up, and you can see here it updated about it. And there's a server running on localhost, so we can sort of immediately view our changes, which is very useful. All right, so let's dig into how we can generate a simple photo blog, for example. And we're going to start actually by deleting everything we don't need. We can delete the About page. We can delete the Cabal file. We're not using it. We can delete the contact page. There's a bunch of templates. We don't need this. We don't need the post list, and we don't need the post. We're going to keep the default template, which is just like the main wrapper that goes around all of your HTML. So as you can see, that's also fully customizable. There's like some best practices in there, so I'm going to leave those there, but I'm just going to delete the links to other pages except for home. And then the posts, I guess I don't need them, and the images, I also don't need them. And we're just going to simplify this even more. So now we only have the index page with hello world on it. So I can delete also all the relevant rules here. So we kept the CSS. This can be deleted. And we basically delete everything except index. And now everything neatly fits almost on one screen, which is nice since we're using a Beamer. Okay, so let's regenerate the site again. So while Haskell can detect changes to your content, like if you make a change to a post or a certain page, we do a proper incremental rebuild. But unfortunately, we can't really detect changes to the syntax in the site.hs file because that's a very hard problem. So if you edit that, you might have to do a full rebuild. There we go. And now we have a much simpler site we can work off. Okay. And I'm going to cheat a bit and copy some pictures over from somewhere else. So now I copied in some pictures, and we're going to start by copying these over, and we can actually simply use the copy file compiler as well. And now we need to edit index.html a bit. And we're going to talk a bit about the templating language that Hakyll uses. So in Hakyll, you can, in your template, refer to various fields or properties of your content. And the way that works is you have a context. And a context is actually a mapping of your actual content to what you will see in the templates. For example, here we had a context for a blog post. We can actually remove this, but it gives us the default context, which gives you some fields like the URL, the title, and then we have a field that renders the date in a specific format. And we're going to write a new one for the index based on what we copied. This parameter is just what the body of the page is. In this case, it's just a string. So for the index, and we're going to use the nice monoid instance for context, so we can compose a bunch of things. For example, we can set title to home, and then if we quickly switch to like the template, you can see, for example, title is used here, right? And the title HTML tag, and this is how it gets plugged in. And then, yeah, I think we use title again somewhere else. For example, here in the H1 as well, in that header. So we have one thing we want to add. We use default context as well. This gives us the URL and some other things. The context monoid works in a way that we can override things. So for example, if default context had a title already, we simply override it here. And then we have one more complicated field. We're going to use a field called pictures. It's going to need a picture context. And so pictures is a list, in fact. And this list consists of calling load all on every picture. Wait, let me only take the JPEGs here. Yeah, so here we have list fields, which means we're going to fill the field pictures by loading all the pictures. So as you can see, we've already sort of created a dependency here. First, we want to generate all the pictures, and then we want to put them in this field. And this context here is simply a context how to render the sub items in the list. And we can just edit the post context a bit. So we make this, because we're building a simple photo block instead of a normal block. So we have the date field, and we can't use, so this is no longer a string because we're using the copy file compiler, so we will need to use this. And then instead of using the default context, we will use also the sweet monoid instance. And here we will just put the URL in a field called URL. And if everything went fine, we should now have a list of pictures, and then inside we should be able to use date and URL. So let's see if that works. So we compile the site, and we can do a simple build. As you can see, it triggered the copy file. It didn't build index for some reason. Oh, so the neat thing is, actually, when I said before that index had a dependency on all the different pictures, files, I was lying. It's only this field here which loads the pictures. So it actually works very nice in like a lazy way. Since we're not using this field in index.html, it doesn't even attempt to load the pictures, and we don't get the dependency at all. And how that works, I'm going to explain later. But let's start by using them. So in the templating language that comes with Haskell is fairly powerful. You have some conditional constructs like for and if, and you can even add your own functions to it from the side.hs. So like if you want to do really complicated stuff like internationalization, those kind of things, you can build your own functions for that. In this case, we just want to loop over the pictures. Yeah, so the syntax of this templating language is inspired by the templating language that's built inside of Pandoc, because some people want to reuse the templates, and since Hakyll is so tightly coupled with Pandoc anyway, that's fairly useful. So for every picture, we want to have the picture itself. Maybe we can create a link to it as well. That's always cool. And then we can have the date. Yeah, so date and URL were the two things I added. And then I just need to quickly cheat a bit again, because I need to update the CSS again. There we go. So now if we compile this, now hopefully it should pick up the dependency and also regenerate index. So it did that, and it didn't regenerate all the pictures because we all already have those. So that's cool. Let's look at it, see if it worked. Yeah, and there we go. We have like the dates here in our format, and we have all the pictures. We don't have pagination right now. I don't think we'll have time to add that during this tutorial, but it's possible. And if we wanted to show one more quick feature, for example, one thing you can do is every post in Haskell has metadata. So every page, and usually it's sort of right here in a prelude. Obviously, we can't really do that for JPEG files. We can't really start editing those and put like a block in front of it. So if we wanted to add titles to the JPEG files, there's two possibilities. The first one, which we're going to use, is simply have an additional metadata file, which tells you something about, oh yeah, exactly, so you can't edit those. But like a second way to do it would be to put like something in the EXIF tags or something of the JPEG files, and then get that out with a Haskell library. And I've written that code, but I'm not sure if we'll get to that, to showing that today. But like, no, actually. So let's add a file here, for example, this one, and by just using the same file name, but ending it in .metadata, Haskell knows what file we're talking about. So in this file, we can just put another title, like, since recently this is full YAML, so if we wanted to add like a list here, this is totally possible. Like, it doesn't really serve a purpose for now. But like, this is used if you want to, for example, a good use case if you want to associate tags to blog posts. You have multiple tags, so you can just use YAML for that. And then here, let's show some more of the templating stuff. And so if we have a title, oh, we don't need it here. We will get, we will just use the title as a caption. And then else, if we don't have a title, we will just use the date. Now, one more thing we need to do is title doesn't really refer to anything right now. It's in the metadata, but as we can see, it's not in the context. And as we said before, context is like a mapping of the actual content and metadata and whatever to what you want, right? Because it's possible that you don't want the title field there. So fortunately, there is this one cool trick. So the metadata field is actually sort of a field which allows you to access everything that's in the metadata. So if we add that, we should be good. And since we edited the site, we should do a rebuild. And yeah, let's look if that works. So one of them should have a title. Okay, there's a title here. So yeah, I'm going to interrupt the demo now and go back to the talk for a bit. But I hope I've convinced you that building a quick website in Haskell is very easy. We did it in like 15 minutes, and we built a photo blog almost from scratch. And there's also tons of tutorials out there. So let's go back to the slides and talk about the internals for a bit. Dependency handling, which is a pretty interesting topic. There's generally like two big questions in dependency handling, at least for Haskell, and it's useful to split them out a bit. The first one is relies to just if you do a build from scratch, there's a specific order in which you want to build things because of dependencies. The second question only applies to if you do a build a second time, like if you edit a file and then build a second time. Maybe you only want to build a few items like the out-of-date stuff, do proper incremental build. Yeah, so first let's talk about scheduling items. Item is the term Haskell uses for everything you build, right? Like a single image or a single blog post or a simple page or a template even. So templates in Haskell are nothing special. They're just another item which you can load and then use. So this, for example, would be the dependency tree of our simple photo blog. So we have index.html, and we rely on the default template, and we rely on 2 pictures in this case. So, for example, this would be a good scheduling order. First a.jpg, b.jpg, then the template, and then the index. Of course, there are other options as well. The important thing is that these go before the template, right? Because otherwise, if we're compiling index, we won't find a picture or we won't find a template. And in this case, that will come down to like we're only using the URLs, for example, of the pictures in the index, but we're also using the dates. So you wouldn't be able to find those dates. So how do we do that? There's no, as we said before, like it's sort of a declarative language. So there is an order here, of course, in which we do things. But for example, index.html is in front of the templates. And actually, we want to do the templates first because index needs that. Yeah, there's no order information, so we need to figure it out as we go. And how does that happen? The simplest approach you can sort of take for dependency handling in build systems is you can just specify everything up front, like in a Unix makefile, for example. You just have a list of all the dependencies. And early versions of Haskell were based on that. We were using arrows, which is also like Xmonad, a design pattern in Haskell. But because firstly, arrows are very cumbersome to work with. And secondly, because you had to specify dependencies up front, even though it was implicit in a way, and I tried to make it as convenient as possible, it still wasn't very nice, because you can't do things like this. It's a bit like the choice you have between monad and applicative in Power. It's a similar design choice between monad and arrow. And here I have some code which, for example, could fit into a context. Like if you're writing a blog for your company, so you have different authors for different blog posts, and you want to include a short bio of the author corresponding to the blog post. How do you do that? Well, you would have different files for every author which contain a short bio in Markdown, and then this is the code that compiles a blog post, and you would first take the identifier of this blog post, and then you can look in the metadata for this blog post, who the author is, and would say, for example, Jasper, and then we get that in author path, and then we would do a load here of the other file. And the interesting thing here is that the dependencies of the item, there's no way we can know them before we actually build this page, right? So we need to sort of start building this page, and only then will we be able to evaluate what the actual author path is, and only then we will need to know what the dependencies of this item are. So we need to do some partial build. Okay, we have this dependency. We need to inject that. Yeah, so let's dig into how that works. Yeah, the advantage, of course, is that this approach is way more flexible. And unsurprisingly, we can solve this in Haskell by having sort of AST and an interpreter for that AST. So this is what it looks like. So compiler is sort of the monad the previous functions we saw are in, like field, like the panda compiler, basically everything we saw, and this is like a simplified representation of it. There's a compiler can have a result, so it's either done or an error. Those are fairly simple. And then there's a third option. A compiler can sort of block and say, I need to have this item, which would be an identifier. So for example, our index page would block using this constructor, and it would say, I need the default template. And then the second is another compiler, which tells you, okay, once you have loaded or done that item, this is how you continue. And then you have a wrapper around this. And actually, you could refactor this quite nicely using the free monad, but I didn't know about free monads in 2009. But that would be a neat refactoring. And let's look at the monad instance for this thing. So return is very simple. And then if we have a bind, most cases are fairly simple. So we look at what's in here. If it's done, we simply call the function on the result. If it's an error, we just stop with the error. And if we have a require, we keep the require because we still need the other item. And we recursively put the bind on how we want it to continue anyway. And then we have, so for every item, we get this compiler AST, which will tell you, I need to do some work, or I'm done. So we need to build a scheduler around that, which tells us what goes first. And so a schedule state can tell you, okay, this compiler is done, or it's paused, and then it gives you the rest of it. And then we have a very simple map of identifier to the scheduled state. And we start by putting everything in paused. And we put the initial compiler, which the user wrote, of course, using like high-level combinators, not using like the low-level constructors in there. And yeah, we start building. And this is what the code for scheduling an item sort of looks like. So we have the identifier of the item we're trying to build, and then the scheduler, which is just the map. we look up if we can find the item. If it's done, our scheduler remains the same. If it's paused, we want to resume this item. So we look at the result here. Then if that actually finishes, that's possible. For example, the pictures in our example would just finish in one time, and we would get a compiler done. Then we record that, so we insert that this identifier is done into the scheduler. If there's an error, we fail. Of course, in the real Haskell code, there's some nicer code around error handling. And if we hit the require, in that case, we actually need to start building this item. The C1 tells us how to continue once we're done with that. So what we do is, instead of continuing to work on this item, we instead start working on this item, and we insert the continuation, in fact, of our current item into the scheduler. And yeah, of course, there's some more things around that. Like, for example, we need to track which items we work on so we can figure out when we're in a cycle. We need to do some proper error handling. When an item is done, we want to write it to the cache, including the metadata. But other than that, there's really not much more to the core of the Haskell scheduler. Yeah, so we finished the first question. How do we schedule things? And like, how can we find out in a dynamic way how to which items to build first? So the second question is, once we've done that and everything is built in a proper order, the user might edit one file and do a rebuild. If we have all of these pause things and continuations, how do we make an incremental build system, right? How do we make sure only the things that need to be built are rebuilt? There's a trick for that. So we have our scheduled state, and as I said earlier, everything sort of starts in paused with the initial compiler provided by the user. This is not really true. We can simply put some things in done already and just load them from the disk, depending on whether or not things are up to date. But basically, if we figure out that something is up to date, what we need to do is very simple. We just put done in there from the start, and we don't worry about it anymore. The question, of course, is how to figure out for which items you want to insert the done already. A big problem. Oh. Okay, I thought you had a question. A big problem is we don't know what a dependency graph looks like at all, because dependencies can be generated at runtime. What helps us, since we only need to solve the incremental build problem for a second build, is that we already have the dependency graph of the previous build, right? So we can use that information, and we can start by assuming it will be similar, in fact. For example, this was a dependency graph I used as an example. Imagine you do a second build and everything is up to date, so nothing gets updated. But imagine the user edits b.jpg, then we also want to rebuild index because it relies on it. That's a very simple thing to do. If something is out of date, we can sort of extend it to the items that depended on it. A bit harder is situations like this, where a new item is added because we didn't really have any info for it. We just knew that index relied on all JPEG pictures, but like, how do we record that? How do we know that, like, if a thing gets added in a specific location, we want to regenerate index? That's a hard question. Another hard question, if we build it, then it gets removed again. How do we track that? We don't really have a modification time for it anymore. It's just gone, and we need to know that we want to rebuild index. So let's solve that problem. The solution is that Haskell stores a lot of stuff to make things faster, like some caching info, the metadata. And in addition to storing the result of a compilation step, So for example, the result of compiling a blog post or whatever. We also store the list of dependencies we discovered during runtime. For example, the first time we run and we compiled index.html, we had these dependencies, right? So we use some sort of writer monad to keep that all, and we push it to the disk. And then if we rerun, we know we relied on those items, so we can sort of look at the modification timestamps for those items. And if one of them has changed since the last run, of course, we also keep the time when we did the last run. Then we know we want to rebuild index. But that doesn't solve this problem, right? Which is the interesting one. So if we have, if we just record a list, A, B, and default, then the user adds c.jpg. Yeah, there's a new file, but we don't really see any changes to the modification times. So how do we do that? So let's go back to the code, and we loaded the list of pictures very late, only when we're actually the list of pictures is only loaded when we're sort of rendering the templates, right? Because only then pictures is used. And here we use the load all function, which is a variation of load that allows you to load a bunch of files. And this thing here is not a string. We use the isString extension. And it's the same thing that's here. And it looks like a shell glob, right? And it is, in fact, something similar. It's called a pattern. We can consider it as like a predicate on all identifiers, which tells you, okay, it matches or it doesn't match. The important thing is that it's not a normal predicate, so it's not a Haskell function. It's actually a data structure, right? We can serialize it as a string. There's some more constructors. So for example, we can do like an AND of two patterns and an OR. So we have another mini language, which we can serialize to the disk, which is very important, and which we can give an identifier, and based on that, we will figure out, okay, the identifier matches the pattern or it doesn't match. So instead of just recording, when we're building index, all of our dependencies, we can also encode which patterns we depended on. Because we're using load all, we get the pattern as an argument. So we also record that here, serialize it to disk, and we also put in the result. So when we build index, we will store that we try to load picture / star, and we will, in the identifier list, we will store the result. So actually, this is sort of what you get when you build index.html the first time. You get these dependencies. So if any of them is out of date, we will do a rebuild. But we also get this thing. And when we do a rebuild, we load this whole list. And we get this constructor. So what we can now easily do is we can rerun this pattern on our new list of files. And then we will get a list in return. If it's a.jpg, b.jpg, we know that nothing has changed. But if an item has been added or removed, the result will be different, right? And we can detect that. And at that point, we will know that we need to rebuild index.html. Yeah, so that's the conclusion of that. And the interesting thing here is that there's also a choice in how powerful you make pattern. Because for example, we have some simple AND and OR constructors, but you could also allow it to look at the metadata of the page or do other things. The only thing to realize is how the more powerful you make it, this is something you need to reevaluate on every incremental build, right? So you also don't want to make it too powerful, because then you will have to execute too many things on an incremental build. So it's a tricky trade-off. But yeah, that sort of explains how we can build like a neat mini dependency handling DSL. I think it's fairly similar to what Shake uses, for example. And yeah, the core of Haskell is really not much more than that. Unfortunately, you don't need to worry about doing the dependencies manually, since we can use all these high-level combinators. So thanks for listening, and if anyone has any questions, we have 8 more minutes, so I would be happy to answer them.